Thank you very much for the kind introduction, and particular thanks to the organizers, especially Praneeth, for his kind invitation to speak here and give this tutorial. It's always a great pleasure to be back here. This is probably my nth visit to ICTS, and every time it's very nice. Today I'm going to talk about strongly correlated particle systems. Of course, this is a very old topic, and much has been said and done about this topic. But today we will look at strongly correlated particle systems through the lens of them being a toolbox for machine intelligence. Okay. We will not assume, given the preponderance of students in the audience, we will not assume too much by way of background. So today, mostly it will be sort of more of a high-level overview where I will try to lay out the landscape of what is there and what is interesting, or what are the things that I find interesting in this landscape. And then in the next lecture, I will try to delve into the details of the how and why of some of these things work, how and why some of these things work and deliver good results. Okay. And as usual, at any point of time, if you have questions, please feel free to stop me and ask. Okay, good. So what are we talking about when we think of strongly correlated particle systems? So without further ado, let us lay them out in pictures. And I would encourage you to go back to your high school days and when you were studying physics or physical science, as they used to call it in our high school. And we were taught about ideal gases and then real gases, a lot about ideal gases, a little bit about real gases. But ideal gases were the nice ones. So they are, it's a collection of particles which are moving around without any interaction among each other. And you could sort of compute various quantities explicitly about this kind of a gas. More real gases were harder, and on the right hand side we have the simulation of what would be so-called Coulomb gas. So here you can think of the particles as let's say electrons, and they are moving around in this jar. So of course we know that electrons repel. So stark departure from ideal gases. So the electrons see each other and they repel each other. Every pair of electrons repel each other, and the repulsion is long range. And imagine that these are kind of put inside a confining potential, so a confining volume, a box, let's say, by the experimenter. And so these particles cannot fly off to infinity, so they basically have to jiggle and kind of stabilize in this kind of a configuration. Okay. Of course, you can we can think of them from a more mathematical point of view, and you can think of the left-hand side as a so-called Poisson point process. For those of you who are not familiar with that term, I will come to it in a moment. The right-hand side is, you can look at it in various forms. So there are various kind of models which capture this kind of behavior, and indeed, it is one of the objectives of our tutorial to kind of delve into and understand some of these models. So these models are going to come in detail later. But first about the left-hand panel, so the ideal gas or the so-called Poisson point process. So what does it entail? Probabilistically speaking, these are particles, or these are points which are sampled independently and uniformly from each other, from this domain. And when you think of when someone tells you, an independent a uniform sample of points, you would imagine something very homogeneously distributed, like that of a grid, like a grid. It turns out that in reality that's not the case. And in reality, if you sample a bunch of points uniformly at random from this box, from this square, you will actually get a picture which typically looks like this. So notice that the distribution, the spatial layout of points is very non-homogeneous. So there are big clumps of particles here and here, for instance. And then, there are, and this happens at all scales. So there are smaller clumps. And then it is interspersed with large vacant spaces. Okay. On the other hand, the electron gas, the Coulomb gas, this is very different. So this actually kind of probably corresponds to something that is closer to your idealized vision of how a uniform distribution of points should look like. In fact, it is actually spatially much more homogeneous. And there are actually mathematical ways to quantify these notions, these ideas. Okay, so this is kind of the basic difference and a little kind of refresher from your school days. Now let us jump closer to business. So the left hand side, the so sort of the independent sampling, independent uniform sampling, that's actually close to that actually corresponds to what we call the IID paradigm of randomness. So this is, as you all know, this is the independent and identically distributed model of randomness. It is probably the most popular model of randomness in science. It is tractable, it's interpretable, it's very easy to handle, I mean, depending on what you are trying to do with it. But for most purposes, it is pretty tractable. And it has led to many foundational ideas and methods in machine learning and statistics. Okay. And the question is there a real benefit to exploring anything beyond IID? And even if there is, would it be realistic? So these are kind of the two broad questions. And of course, in nature we see many kind of processes and systems which are not really IID. But if you look at them closely, you will see that the IID structure is actually violated in very simple and very structured ways. So one simple example would be, let's say, a Markov chain or a Markov process. Okay. Yes, if you take a sequence of observations from a Markov chain, yes, they are not independent, they are not IID. But there is a very structured way, and in which the IID structure is broken, and then then there are various methods like the Markovian decomposition of probabilities, by which you can actually reduce to something which is not that, which doesn't look that far from independence. Okay. But when we talk about strongly correlated particle systems in this tutorial, what we have in mind is really correlation or dependencies that are much more complicated, that are much more complex, that are dependencies of all orders, and that actually kind of imitate much more closely the real world particle systems that are found in nature, for example, in electron gas. Okay. The other part is also, the other question, being realistic, is also important, because at the end of the day, if you want to utilize these kind of models for doing machine learning, then the question is, how practicable they are from a computational point of view. Okay? So we'll try to look at some details and some answers to these questions as we go along. In the context of the first question, what we just discussed in the first slide, the lack of spatial homogeneity in IID sampling. So this immediately leads to an issue that IID samples may be less representative or less stable. So how so? So imagine that you have a function, and you want to integrate that function over this domain. Okay, you want to compute the integral. What you want to do is you want to use Riemann sum, and you want to use these, for example, as the nodes of your Riemann sum. Okay. Now you immediately land up in a problem, because depending on, of course, if your function is constant, for instance, if it is very simple, then it doesn't really matter what are your nodes here, right? Because it's the function is the same at all places. But suppose your function is actually very far from that and it has a lot of fluctuations. So then, depending on your luck, how your random point set, how your random sample looks like, if your function has very important behavior in one of these vacant regions, this particular sample will totally fail to capture that. Okay. On the other hand, suppose your function has some turbulent behavior, but only in a small part of the domain, which is probably not that important for the overall integral. But maybe as luck would have it, your particular IID sample has a lot of points focused in that small turbulent region. Then this can artificially distort your estimate of the integral. Okay. So this is an issue. So IID samples may be less representative. So there could be representativeness issues. This is one. Another issue is this. So to sort of describe that issue, let me kind of preface it by saying that these two simulations, they have been normalized in the sense that the total number of points or the average density of particles per unit area is the same on the left and right panels. Okay. Now, if that is the case, then that would mean that and this would roughly correspond to what is called equilibrium statistical mechanics. So what will happen is that if you take many samples like this, on average they would be the same. Let's say the expected number of particles per unit area will be the same, right? It will be some constant number. That means that if in one particular sample there are big vacant spaces, then in another different sample, IID sample from the same domain using the same model, there has to be a lot of particles in this domain to balance. So that would mean that your samples may be less stable. For example, now if you juxtapose this with the Riemann integration example, the value of the value of your Riemann integral estimate, it can kind of vary widely between one sample and the other, and then it can become very sample dependent, which is something which is not ideal. So what you really would like to have is that you go in and just draw a sample and get your estimate and not have to worry about it too much. Okay. So this is clearly some issues, and generally speaking, the more complex your learning task becomes. Nowadays, particularly with the advent of AI, sampling is very important because the scale of data and the scale of the data sets that we work with and the scale of the models that we work with are both so fast that it is almost impossible to work with the whole thing in every particular iteration, and you always need to work with some subset, some subsample, and therefore as the scale of the things grow bigger and bigger, these issues become more and more important. Okay. What are the examples of some sampling problems that we might have in mind? So one of them is Monte Carlo sampling, which is exactly the problem that we discussed, that you have a domain, you want to estimate the integral against a measure. What you do is that you sample points. In the vanilla case, in the classical setting, you sample points IID from that measure, or as we shall see, sample them using some other method. But you have some sample S, and then you average it over S and try to use that average to approximate the integral. Another example would be sampling core sets. So there is some loss function that you want to, which is the sum over a big data set, let's say. But this data set is too big to calculate this sum precisely at every stage in a computationally reasonable way. So what we want is to just do this summation over a subset of this big set X, a big data set, let's say X, where your subset, where your subset is representative enough in the sense that you allow yourself some flexibilities. So for example, you allow yourself to multiply your values on your subset by specific weights, but you consider this kind of weighted average on your subset, and the subset should be much smaller than the big universal set, and then you want this random variable. It is random because the subset S is random, a random subset of X. You want to use this random variable as a reliable estimator of the full loss LF. Okay. Of course, classically people considered scalar valued quantities. So, for example, your F could be squared error loss, your X could be varying over the data set. On the other hand, you can also think of vector valued quantities where you can think of your F as some gradient, and then what you are interested in, imagine that you are doing stochastic gradient descent and you want to estimate the gradient. Left hand side would be exact computation of the gradient, but data set is too big. You don't want to use that at every iteration. So you want to sort of get away with using a much smaller subset of the data by taking appropriate weighted averages of the gradient. So these kind of problems actually they cover a lot of ground. Then there are other applications which we will not talk about too much during the limited scope of this tutorial, but I should mention it to kind of give you the big picture. So one example would be feature selection. So your goal would be to sample a subset of columns. So imagine you have a matrix, big matrix, but which is low rank. So there are lots of columns, but the actual number of representative linearly independent columns is quite small. So you want to, what you want to do is that you want to sample a subset of columns of a low rank matrix to be representative of the entire matrix. Another example would be neural network pruning. So you have a big neural network. Now what you want to do is that you feel that, or you believe that maybe such a huge structure is redundant, it contains many redundancies, and you want to delete some of the redundant edges from a neural network without compromising too much on the quality of output. Okay, let me just preface this by saying that we live in the era of randomness. So there is no way on earth that you are going to not lose anything by kind of doing this subsampling procedure in any of these examples. But the point is that the goal is to keep your losses within certain controllable limit. Okay, so that's what we are driving at. And for more examples and details of all these applications, you can look at our recent survey. And it contains some new results on neural network pruning, which we put on the archive a few months ago.
Hi.
Yes.
So I have a small question. So you mentioned this application to numerical integration.
Yes.
So I'm aware of something called quasi-Monte Carlo sampling, where
Yes.
The connection is to something called discrepancy. So,
Yes.
so
we will come to those connections later.
Oh, okay, great.
Yeah. There is even one slide related to discrepancy lower bound, if that makes sense.
Excuse me.
Yes.
So when you talk about like evaluating a function on, let's say, ideal,
Yes.
The ideal gas, the IID
Yeah.
case, so we do know.
Yes.
Yes, you get even stronger concentration inequalities.
Yes, that's exactly what I said. Okay. Okay, good. Now, just as if to answer your questions, I have a slide, next one. So for IID samples, the approximation guarantee is usually of the order 1 over the square root of the sample size. Now, okay, I am keeping things intentionally vague here because in every particular application, each of these notions has to be suitably defined, and one has to clearly explain what we mean by this order, the notion of this order. But roughly speaking, you will get a 1 over square root of the sample size approximation. And this is a rate that essentially comes from central limit theorem. Because you make an error in from each sample, then these errors are independent because you're doing IID sampling, and these errors then accumulate. But then if you average them, then like how much do you lose? What is the confidence guarantee? And that's classical central limit theorem. That's So that's the concentration, for example, the concentration inequality version of the simple heuristic that I told you just now is, will give you. For strongly correlated samples, when again, I have not told you what exact strongly correlated model I am using, but for the suitable models that I will introduce, we can prove in various settings that approximation guarantee is often better in the exponent. Okay, and when the scale becomes large, this purchase gives you a lot of purchase. So for example, imagine you are doing this sampling at every step of some iterative algorithm, then all these gains add up over each step of your iteration. So you get a strictly better than 1 over square root 10. Okay. So now, to summarize this sort of enveloping discussion so far, so what have we seen, or what are we driving at? So we are looking at IID versus strongly correlated samples. Suitable strongly correlated samplers provide similar approximation guarantees. So you can try to set these approximation guarantees to be the same, in which case you will see that you will get by with a much smaller M, with much smaller sample size for strongly correlated samples. So suitable strongly correlated samplers provide similar approximation guarantees with much smaller sample size than IID. And this can bring in significant benefit in settings where the function evaluation is costly. So let me give 2 examples of this. So suppose you are doing stochastic gradient descent for highly complex functions. So let's say large scale neural networks. So your function, as we kind of discussed heuristically in the course sets example. So your function is f is a gradient. So your function f is a gradient, and you are kind of averaging this or adding this up over the sample versus over the full data set. So in order to compute any of these things, at every point x of your sample, you need to compute the f. Now your f is a gradient, and if this gradient is from a neural network, then you have to do the entire backpropagation pipeline to compute one gradient. Okay, so this is a lot of cost. So if your s is smaller, then there is a clear benefit. Okay. Another example is large-scale conditional random field models, where also the probability distribution is so complex that you want to compute it as few times as possible. Okay. So now, so I have kind of promised you that there are suitable strongly correlated sampling techniques, which give you clearly sort of better guarantees than IID samplers. So then I have to come good on my promise and introduce them. This is the point where we introduce a key notion of strongly correlated sampler, which also comes with certain tractability, both in terms of the implementation as well as in terms of the analysis. Okay. So a significant class of natural strongly, and we will look at each of these aspects as we go along. So a significant class of natural strongly correlated particle systems are determinantal point processes, or DPPs. They offer a combination of tractability and feasibility. So what is a DPP? We will come back to this in various depths at various points of this tutorial. But at this point, it suffices to say that it is a random set of points. So it's a way of generating subsamples S from your big set X, so that all interact with each other. So there are interactions with all orders, and where the interaction is encoded by a kernel. This is very important because we love kernels in machine learning, because once we have a kernel, we can bring in a lot of tools to deal with them both mathematically as well as in terms of implementation. And DPPs are in a sense the kernel machine of particle systems. And DPPs for machine learning, they have been sort of around for a while. So they have been around for for a decade or so. And over the years, slowly many new results have been added to the arsenal, which have brought us to the point where we can actually make these statements. Okay. Okay.
So,
Yes.
independent samples are very easy to generate.
Yes.
And maybe you're not
Yeah.
accounting.
So I will talk
Documented
about
costs
that.
are very expensive to sample from, right? So you'll account for that.
Depends. So there is always a cost benefit trade-off. Okay, there is a cost and there is a benefit, and the question is what is the right price point you want to pay. So you again think of the situation where you're what you are doing with your sample. So this is one thing about sampling. So rarely do we need the full sample set as a whole. Rarely do we use it as a set. What we do is that we generate this sample, the set S, and immediately we compute something simple like something real valued with it, and then forget about the set. So in some sense, we are doing a much more complicated procedure, generating a random subset in order to compute basically a univariate random variable, right? But in any case, that is later. But so suppose you are computing this summation fx where x varies over this subsample x. Now, of course, there is a complexity, there is a cost to generating s, the sample s, if you want to do it in a fancy way. But on the other hand, there is also a cost to, let's say, evaluating this summation fx, right? Because each fx might be costly to evaluate, as we discussed in various pretty relevant examples. So then, there could be a point where the cost of where the marginal extra cost of generating the sample, generating a strongly correlated sample, would be completely outweighed by the savings you gain by having to evaluate f a much smaller number of times. Okay, so that's the trade-off. Now, the better you do with your sample generation mechanism, better you do with your algorithm, the easier this price point becomes. And I will discuss some algorithms which have come out in the last 2-3 years, which have a lot of improvement over the classical methods of generating this. Okay, so but let us talk a little bit about the origins of DBPs. So DBPs originate in physics. They canonically in quantum and statistical physics. In fact, the way it actually appeared in the physics literature, although it was not called by the name determinantal probability measure at that point, is that if you can in the simplest fermionic system, if you write down the formula for the wave function in its ground state, and obeying all the physical laws like Pauli's exclusion principle, your solution actually has the form of a determinant. And this is in the physics literature, it was it is described as a Slater determinant because from what I understand, it follows from the work of Slater. But it actually comes on top of earlier works by Heisenberg and Dirac. So this kind of determinantal structure is actually known in the quantum physics literature for quite a while, quite a long time. And later, connections to a wide interface of physics and mathematics were developed, including random matrices, random polynomials, random networks, Coulomb gases, and so on. Okay, so this is the kind of the history of the pedigree of this model. But mathematically speaking, it's a very concrete model. So how to describe it? Let us in order to sort of give a more concrete description of a determinantal probability measure, let us take a step back and let us try to kind of understand or recall how we describe a much simpler random variable. So what is the simplest example of random variable that we can think about? Well, let's say it's a univariate random variable, right? Let's say a Gaussian random variable in one dimension, or an exponential random variable in one dimension. So how do we specify them? We specify them by a probability density. So you give me your point x, I will give you the probability density, or if it is discrete, the probability mass function of the random variable taking this value. But here, as we already sort of alluded to in the discussion, we are considering a much more complicated kind of random variable, which is a random set. It's a set valued random variable. So of course, the sort of the basic minimal requirements to describe a set valued random variable will be more complicated. And what it entails, what replaces these probability density function or probability mass functions are these so-called correlation functions. Now, this is a little bit of a dangerous word because correlation functions are all over physics. They come in various shapes and forms. But in the point process literature, it is kind of it has a very specific connotation, which is what I'm going to describe now. So imagine that. So imagine that you are generating the subset from this big square. Okay, and imagine that it is kind of discrete, it's a discrete square, and you want to sort of generate a subset of it, okay? So just like if it was a univariate random variable, then all that I need to tell you is that if you show me this point, I have to tell you what is the probability of me picking this point. If it is a random subset, then what I have to, if it is a random set, then what I need to tell you is that if you show me any subset, then I have to tell you the probability of this subset being selected in my sample, okay? And these are exactly the correlation functions. So a random point set or a random set is characterized by its correlation functions, which are essentially the joint probabilities of having points at those specific locations. So in particular, let's say you take m fixed points, alpha 1, alpha 2 up to alpha m. And then the mth order correlation function is the joint probability or probability density, depending on whether it's discrete or continuous, of your sample containing all these points, alpha 1, alpha 2 up to alpha n. So this is the m order correlation function. But the only difference, the key difference with real value random variables is that you need these correlation functions in principle for all values of m, all integer values of m. Because the game is that you give me a subset and I should be able to give you the probability of that subset being included in my sample. Now this subset can come in any size, and this m is essentially the size of the subset that you specify to. Locations? Yeah, I'm picking a random set from a very big universal set. Now, how do I specify its distribution? So you give me, let's say, 5 points, some 5 points. I will give you the probability of those 5 points being included in my sample. And if I do it for all values of 5, then that specifies that. I mean, it is technically it's not obvious, but there is a very general theory which okay. So what is the simplest example? Again, we have to go back to IID for anything that is simple. So if you have if you have a big universal set and you are picking points independently with probability rho, then your m point correlation function, if you unpack this definition, is just the product of rho m times at all these locations and is rho to the power of m. Now, of course, we are thinking of a strongly correlated particle system. So we are not going to have something which is this simple or this uninteresting, and we are going to replace it by something more interesting. And this is also going to pave the way for the appearance of the kernel. So for a determinantal probability measure, the m point correlation functions for any m are given by a determinant like this. And because of this reason, it is known as, and because of the fact that the correlation functions have a determinantal formula, these are called determinantal processes. And this determinant is of a matrix which includes a kernel, which embodies a kernel. And this is a kernel function that drives the DBB. Okay? Yes.
So I give you n plus 1 points.
Yeah. So there needs to be some conditions on when this is on K, when this is going to define a consistent family of correlation functions, and there is a very neat description of that. So maybe I can discuss a bit about that in the next. Okay. So DBBs are particle systems which are parameterized by a kernel K, and in particular, already from this expression, you can see why the notion of repulsion is tied in very closely with DBPs, because imagine that you have a, so imagine alpha I and alpha j are equal, okay? So forget being close to each other. Suppose some alpha I and alpha j are equal. So that would mean that the ith and the jth columns of this matrix will be equal and the determinant will be 0. So that means that the probability of having a subset with repeated entries, probability of repeating the entry is going to be, in your sample, is going to be 0, okay? Now we can imagine that if the kernel is regular enough, this also holds true not only when alpha and alpha j are exactly equal, but they are close to each other. So you can imagine that if they are close to each other, then this determinant, although non-zero, will be pretty close to 0. So that means that if you look at subsample, if you look at samples where sample elements are too close to each other, then these samples are disincentivized by the stochastic model, okay? So by the sampling scheme. Okay, so this is the, and kind of the notion of repulsion is important because this is the reason, the repulsion is the crucial physical reason why DPP samples or why the strongly correlated negatively dependent samples look like the way they do. So let us go back to the original slide, starting slide. So if you look at this, so if you think of these particles to be repelling each other, then actually you can pretty quickly come up with a reasonable physical heuristic for explaining why they are so spatially homogeneous. Because these particles, they are repelling each other, so they cannot come too close. So they are trying to move away, they are trying to fly away. So if there was no barrier, they would fly away to infinity. But in any real world experiment, there would be a barrier, there would be a confining potential. Let's say, you just put the gas in some physical box or something. So then these particles cannot fly away to infinity. So they cannot get too close, they cannot get too far. So they are forced to equilibrate pair by pair in this kind of intermediate location. So that's why the interparticle distance is much more stable. Okay. Okay, so so before the talk, it was discussed that I should give a short break at some point. So maybe 36 minutes and 32 seconds are remaining. So maybe this is a good point to give that break. So maybe we reconvene in like 5 minutes. Okay, so just before the break, we saw what determinantal probability measures are. They are random sets. So a random set is characterized by its correlation functions, and these correlation functions are given by determinants of a kernel function. This kernel is kind of the driving parameter of the determinantal process. And because of this determinantal structure, automatically repulsion is baked in. And we discussed that repulsion is the key kind of the heuristic or the in principle reason which makes these samples so well spread out over space. Okay, so DPPs are therefore effective in modeling situations where sample points are desired to be very different to each other. So either for modeling or if you want to generate samples which are very different from each other, then these stochastic models give you a clear advantage. So for example, in diversity sampling, population is represented by points in some high dimensional feature space. This is the space in which X lives, and then the kernel K should incorporate the proximity between these points in feature space. So you can think of for example, an RKHS type of scenario where K, X, Y is just the inner product between these feature vectors. And this in turn includes the similarity between the points in the ground set we want to sample from. So you can use a DPP paradigm based on this suitable kernel K, and the samples will generally reflect the kind of diversity you want in your random subset. And applications, as we all saw, it includes feature selection, Monte Carlo integration, coarse set selection, and we'll come to it later in the tutorial, dimensionality reduction. And as I already mentioned, our survey actually includes detailed discussion on each of these applications. So in each application, somehow the stochastic model has to be tailored. It has to be applied in a specific way in order to give you the most optimal results. And we discuss the details there. Here we will stick to more fundamental discussions. Okay, so now I want to discuss a little bit about sort of a more concrete version of the promise that I made you, that you will get this kind of fundamental improvement at the level of the exponent. So of course, in general, if you just start with some arbitrary kernel k, you might not, in general, I believe you would not get such a clear improvement. So there has to be a general technique or a general setup, a general approach, which can kind of reliably give you that sort of. So this brings us to orthogonal polynomials, which is another very classical topic in applied mathematics. So probably so imagine you are on a Euclidean space and you have a probability distribution gamma on the Euclidean space, and you can look at monomials in graded lexical order, and then you can apply the Gram-Schmidt algorithm in L2 of gamma to these ordered monomials. So for a simple example, for anyone who has not seen this before, just think of dimension 1. So you can think of the power functions, and suppose you are on the interval 0 to 1 and you have some measure mu on the interval 0 to 1, and you can look at the polynomials. Okay, so these polynomial functions of course carry a lot of information, and what you want to do is to but they are not very suitable for various purposes because they are not orthogonal under the measure mu. So what you do is that you orthogonalize them. So, and using the Gram-Schmidt algorithm in the Hilbert space L2 mu. And once you do that, you will get a different set of polynomials. So this is a sequence of orthonormal polynomials. And in general dimensions, in one dimension it's univariate, in general dimension they will be multivariate orthonormal polynomials. These are called orthogonal polynomials. So that's a simple gist of the story. And these are actually very classical tools and objects in applied mathematics as well as mathematical physics, and therefore in various important settings orthogonal polynomials have been studied very intensively. And this in particular means that there is a very vast toolbox of highly sophisticated methods in order to analyze, in order to do analysis with these orthogonal polynomials. And time permitting, we will see, some ingredients from that toolbox, how it helps in the context of these sampling problems. But the moral of the story is that once you use a very classical object like this, like orthogonal polynomials, you are immediately in a position to leverage all these classical tools and techniques. And of course, in terms of DBPs, we want a kernel. We want to talk about a kernel, and this kernel is essentially given by a projection onto these. Let's say you take the first m orthogonal polynomials, and you consider the projection onto the space spanned by orthogonal polynomial, those orthogonal polynomials. And remember that if you because of the structure of the Gram-Schmidt algorithm, the space spanned by the first m orthogonal polynomials is also the space spanned by the subspace spanned by the first m powers. Okay, so it's the same space. You are looking at the projection. You are looking at the orthogonal projection onto this space. Okay, and this gives you a kernel. And see that we are already kind of generalized, gone into abstraction, because we are now looking at kernels and projections, which are essentially in infinite dimensional spaces. Okay, but whereas some of the initial motivating examples that we studied, we were thinking of generating random subsets of a big finite set. But the advantage of DBPs is that it allows you to switch seamlessly between these two worlds, finite and infinite, without much hassle. Okay. So the type of model that we will be looking at is orthogonal polynomial models, or so-called orthogonal polynomial ensembles. So an effective choice of kernel for sampling applications is given by the projection onto the space of orthogonal polynomials. Okay? So you decide what degree of the orthogonal polynomial, what power you are going to go up to, and you take the projection operator onto that subspace, and you look at the kernel corresponding to that, usually constructed like this, and that's your that's the kernel of your DPP. Now, one can immediately ask as to how to choose M. So there is a very simple correspondence between M and the actual point set that you know, some aspects of the point set that you realize in the DPP. So in the case of orthogonal polynomials, the M you choose here is going to be the size of your random subset. The size of your random subset is going to be almost surely a constant, and this constant value is going to be the M here, and this is deterministic. So this is another kind of advantageous aspect of using kernels like the orthogonal polynomial kernel, because then you get absolute certainty on the number of samples you are going to generate. So this is in practice, this can be a useful situation. You do not want you know, you do not want a situation where your sampling technique typically returns you something close to 100 samples, but it can become one sample if you are unlucky. So you do not want to do that, and orthogonal polynomial kernels actually kind of assure you that you are not. And in fact, it is not necessarily, it does not need to be so specific as orthogonal polynomials or so structured as orthogonal polynomials. You can, in general, any kernel which is a projection is going to give you a fixed number of points. Okay. So what are some advantages of using orthogonal polynomial kernels? So computing OP kernels is equivalent to computing the moments of mu, because essentially you need to, in order to compute this kernel, you need to know the coefficients of your orthogonal polynomials, and these coefficients are given because of the way these orthogonal polynomials are generated by the Gram-Schmidt procedure. So they're essentially, what you are computing is inner products of these polynomials. So these are the various moments of your measure mu. So so this OP kernel, the construction, the computation of this OP kernel is essentially based on the construction of the moments mu. That's all that you need. And this is good because there are in a real world situation where you might not have, you know, access to the full measure, but maybe you only have a large sample, then estimation of some low degree moments can be done much more effectively, rather than trying to compute something something else that is more sophisticated about. Okay. The rank of oops. Yes. For example.
So you're assuming that you have as many moments as the sample size.
Yes.
So say that I want to get sample size 100,000, you need 100,000 moments.
Yes. But no, but the point is that your computation of moment is once for all, right?
Okay, but say that is in 5 dimensions, so it's
no. So here is a crucial point. You do not need all moments of up to degree 100,000. You need 100,000 marginal moments. Let's say
the sum of the exponent to be 100,000.
Yeah. So let's think of moments of order 2. Okay. So what you need is so let's say in d dimensions there are it's a d by d matrix, right? A covariant matrix. So there are total d square there are marginal moments. So if you need m moments, if you need dimension m points, then you need to know, let's say, m of these d square moments, not m square. Yeah. Yes.
If you're doing stochastic gradient descent,
But you have a sample.
These moments are just the sample estimates of these moments?
Yeah, that's what I said. That if you want to compute something very sophisticated about a distribution, then there is a room for a lot of error, or estimates might be hard to get or unstable. Moments are more basic. So particularly if you stick to low degree moments compared to your dimension, then they are more basic. So for example, let's say in a stochastic gradient descent scenario, typically you want a small sample, not a very big sample. So by the way, so I would like to preface this discussion by saying that I am not presenting to you the silver bullet which has solved the problem of sampling in various machine learning applications. I'm just trying to suggest an alternative to the usual paradigms, which I believe that, or we believe that if it is investigated in the right directions, can lead to very fruitful results. And in particular, many of the guarantees, for example, which I already alluded to, and I will present in more detail in the later parts of the tutorials, actually, many of these guarantees were obtained only in the last 4 or 5 years. So before that, practitioners used to try to use some of these repulsion-based methods in an ad hoc and heuristic way without any theoretical substantiation. And these guarantees, these m to the minus gamma, for example, these are the first theoretical results which actually substantiate the effectiveness of this method. Okay. Okay, so so the rank of the kernel is equal to the number of moments needed, which is the sample size, and this can naturally be extended to reproducing kernel Hilbert space of approximating functions. So if you have an RKHS and if you instead of the orthogonal polynomials you take the RKHS some suitable RKHS basis functions, then most of the story can be repeated. Okay, so here is a kind of a more substantiated version of the improvement in approximation guarantees that we discussed. So if you have orthogonal polynomial based DPP sampler, then it gives you approximation guarantee that is so if you were doing IID sampling, it would be order of sample size to the minus half. So here you have an here you have an exponent that is bigger than 1/2, and the increase is by 1/2D. So naively, D could be the ambient dimension, but in actuality, the D can be taken to be the reduced dimension of the data. So we first pre-process the data with, let's say, some simple linear dimension reduction technique, and then do the DPP sampling in that dimensionally reduced space. Okay. So in practice, this D need not be so big. And we also have packed guarantees of the same order up to log factors for several specific ML applications. So this is a little bit application dependent, whereas this is more general. And the overall take-home message is that DPP is a fundamentally Hilbert space-based technique, and we will come to that later when we discuss sampling in more detail. So it works very well with linear projection-based dimension reduction method. So always we would recommend doing a linear projection-based dimension reduction and apply the DPP after that pre-process. Okay. So what about regularity and rates? So this is for a pretty general class of functions, but better rates than these are possible for function classes with specific smoothness properties using RKHS techniques. So function classes, so RKHS functions which form an RKHS, which belong to an RKHS, generally have improved smoothness properties, and those can be translated into better rates. Okay, for example, this could be replaced by the rate of decay of the spectrum of your RKHS kernel. Yes.
Is there more sensitivity to noise?
Noise in what? I mean, I don't see how it can worsen from independent sampling scenario. I mean, if there is noise in your data, it is also there for independent sampling, and then you are doing extra noise over that. What we are trying to say here is basically in the subsampling stage, you are adding less noise. And the interplay between smoothness of the objective function, let's say, which you want to integrate, and the rate of the DVP approximation guarantees, it remains to be fully understood. So this is what. Okay. So here is some discussion on concentration phenomena. So here we have stated the general result using vector valued function, but for simplicity, imagine that you are in this integration example, and your lambda m is the kind of a sample average, and your expectation lambda m is the integral, and you want to, and everything is one dimensional, so there are no knobs. There is just the absolute value. So then, if they were IID samples, then this is like the Wavering bound, right? And then you get something which is of this form on the right hand side. This is the concentration guarantee, and you will get the variance here, right? So sorry, that is like the like in the Bernstein type of situation. But that's known for independent sampling. And then if you have a vector value test function, so if you want to sort of obtain guarantees which are not valid just for one single test function, but a bunch of them together, so you can stack them up as a vector, and you can write a concentration inequality like that. But that is kind of from classical techniques in the setting of IID sampling. For any kind of correlated sampling, getting anyone who has worked with concentration phenomena will tell you that getting a concentration of measure inequality like this is it's very complicated, and usually it's not possible, because the correlations, it's very hard to parse. But in the setting of DVPs, and this actually sort of brings us back to the advantages of DVP, because it has a very clear tractable mathematical structure in addition to geometric interpretation, and this tractability actually translates into the fact that we can obtain clear concentration guarantees, concentration bounds like this. And notice that the concentration is in terms of the variance, which is so here, for instance, if you had IID samples, you will have a similar concentration guarantee, and your variance will be n, right? You will get a concentration guarantee of epsilon square over m. So here, because this quantity is better than 1 over square root m, you get something strictly better. So I think someone asked whether these bounds are, this improvement is only at the scale of the CLT, or does it carry over to the level of concentration? And the answer is yes, and the inequality is here. Okay. So let me just sort of abbreviate the inequality and comment a little bit about it. So concentration and strong dependence. So this is an example of a concentration phenomenon with a structure that is quite similar to concentration of measure inequalities for independent random variables, but it is valid in the context of strongly dependent stochastic model. So this is a rarity in itself, and it underscores how DPP blends strong dependence with structure and tractability, which allows for such powerful results. And notice that much work still remains to be done here, and I will comment on the technology which allows us to derive this kind of strong concentration inequality in the next lecture. But let me comment that much work still remains to be done. So, for example, if you look at this concentration inequality just from a pure probabilistic inequality point of view, notice that it is valid only within a certain range. Now, this range is good enough for us to derive the pack guarantees in most of the applications that we considered, but But as an inherent probabilistic result, this is not fully satisfactory. And we believe that boundaries can be pushed here. We just don't know exactly how. I mean, so we have a technique. I'll try to explain a little bit in the next lecture. And at some point, the analytical method just gives way. So this is where we stopped. Yes. Write your paper. Write your paper. No one knows. So this is the result from last year. So I mean, you're welcome to investigate that and please cite our paper. So yeah. So and again, on this point, I would like to again emphasize that almost any interesting question you can ask about these models, they are A, not known, and B, probably they are amenable to some reasonably interesting theorem. Okay, you just need to try. Okay, very good. So let me comment a little bit about the generality of structure and scope for DBV models, and this we were just discussing during the break, just before the start of the second half of the lecture. So DBV samplers provide representative samples in very general settings. So this includes complicated geometries or even discrete or combinatorial or non-geometric background spaces. Because the entire thing that underpins this model is this kernel, K of x, y, and all computations that you do is in the space of the kernel. So your x and y, they can be like very, very abstract, very abstruse objects without any inherent geometry. Okay. So other methods, and this again brings us back to your question. So other methods such as grid points or specific types of low discrepancy sequences, they are very specific to simple geometric settings such as Euclidean spaces. So for example, as soon as you go from Euclidean spaces to, let's say, something mildly, which has a mild geometric structure like a sphere, the concept of what is the right notion of grid becomes subject matter of debate. And then, as you scale with the dimension, these things do not scale very well. Okay. And they may scale poorly with dimension. And but on the other hand, DBV samplers provide a notion of a stochastic grid pattern. So this grid-like point distribution, when there may not be any geometry to support the notion of a grid. So in some sense, it is your grid when you cannot naively define a grid. Okay. And the other point which I would like to emphasize, and this we also came up in the discussion during the break, is the power of abstraction. So why a DBV is able to handle such abstract spaces without geometry? It does so by looking at not the space itself, which doesn't have structure, but it looks at the function space on top of that, or which lies on top of that space. So just take the orthogonal polynomials as an example. So suppose I tied my hand and I did not want to use the geometric structure of the Euclidean space. But the DBV doesn't really use that. It does what it uses is these orthogonal polynomials and the projections in the space of orthogonal polynomials. Or you can think of RKHS, and RKHS can be defined in very abstract settings. So the abstract setting, that space, underlying space, it might not have any suitable geometry, but the RKHS has a very clear linear geometry. Okay, and because it looks at this function space structure, it brings to bear many tools from Euclidean space and Hilbert space theory. So that's the kind of advantage. And we will see a more clear kind of manifestation of this, of the Euclidean geometry, of the Hilbert space geometry, when we come to the question of
naive question. If I was to throw points in a hypercube,
yes.
If I throw random points, I can do it sequentially.
Yeah.
How hard or easy would it be for these processes to?
These are also sequential.
And easily, it's not.
Yeah. I'll discuss that.
About that.
Yeah, I don't know. We have a slide and some more details.
So conditionally, the next point depends on the configuration that's already there.
Yes.
I have to take that.
But that update is very clean. It's a linear algebraic update. So the whole point is that it reduces everything to linear algebra. So the update, the conditional distribution. So okay, let me give you a quick summary. So the whole point is that if you take a DBP and you pick one point from that, and you condition your DBP to contain that point, then that conditional point set, which will contain 1 point less, is another DPP with a kernel. And this kernel, this new kernel, is a rank 1 update of the old kernel. So this brings all these linear algebraic tools.
So that's the way to generate typical.
Yes, yes. I'll discuss the details. Okay. Another conceptual point which I would like to emphasize is the power of the second order effect. So for all these improvements in the exponent, for example, that we saw, it is important for the sample points to see each other for the improvement in the exponent on m. So, going from m to the -1/2 to the m to the minus gamma, where gamma is bigger than half. In particular, interactions must be at least 2 body. So what do I mean by this? So suppose not. So suppose I have a sampling scheme, which is very clever, but it doesn't make the sample points look at each other. So the probability of having one particular sample point doesn't depend on whether another point is in the sample or out of it. Okay, so this is like sample points do not see each other, and then you can be very clever about it. And what you can do is that you can kind of reweight your sampling scheme. So if you are an important person, I pick you with more probability. If you are a less important person, I pick you with less probability, and you can do various versions of this. This idea actually has this basic idea. It has been very effective in sampling theory, and it leads to various versions of what is known as importance sampling. Okay, and importance sampling actually does improve your approximation guarantees, but usually what it does is that it improves the constant in this big O. Okay, whereas in order to obtain an improvement in the exponent, you really need your your sample points to see each other and depend on each other being selected. Yes. Same as yeah, it's independent, but within independent also you can be very clever, because you can choose a very optimized weight profile of, independent doesn't need to be identically distributed, right? So you can choose a very clever and optimized weight profile, whereby different data points have widely different probabilities of being selected in your sample. So that's exactly the basic idea of importance sampling. And then the whole game is how do you optimize this weight profile? But usually that leads to an improvement in the leading constant, not in the. And it is crucial that the kernel K is a projection operator for DPPs. Otherwise, the fluctuations can be Poissonian in nature and usually of similar order as importance sampling. So this is a somewhat technical point, but what this is saying is that if you want a result that has this improvement in exponent beyond 1/2, then you have to have your kernel to be a projection. Okay. So that's about it. Yes.
So in M is order D.
Yeah.
Typically, then D to the 1 by D is a constant. So then importance sampling and this are sort of taken.
Yes, but the point is that usually the ambient dimension is very big, but the real dimension in the data is typically much smaller, because that's the structure in the data, right? We believe that in real world there is structure in the data, so the real dimension should be small. So we do dimension reduction first and work within this dimensionally reduced space. Now one can argue that, well, if you dimensionally reduce data, if you dimensionally reduce the data, then this might screw up the DPP sampling structure, but that doesn't happen. That's because of the Hilbert space theory. Yes. Yes. So as I alluded to earlier, these results are the first ones for any kind of guarantees for DPPs. So this is where we could do it. It doesn't mean that it cannot be done elsewhere. And actually from experimental results, it seems that it is more general. It's just that, and even you can do like things like discrete orthogonal polynomials, which are actually much more convenient with computations. But the point is that we cannot prove them. But that, that will, if you're a practitioner, that will not stop you from actually using it. Okay, so the next question is that of sampling from DBPs. So let me just give you the give you the very basic picture, because 3 minutes 19 seconds are remaining. So the algorithm to choose to select generate a sample according to a DPP is a spectral algorithm, and to my knowledge, this traces back to a paper by Huff, Krishnapur, Perez, and Virag, which came out around 20 years ago. And essentially what it does is that it interprets this determinant of this matrix. Imagine that you are in a RKHS and your KX, IXJ are inner products between vectors, and these vectors are the sides of this parallelepiped, okay? So then what it relies on is that it interprets the determinant of this KX, IXJ, this probability, as the squared volume of this parallelepiped, and everything is downstream from there. Now in less than 2.5 minutes, I will not go into the details of that, but we have the next lecture for doing that. But let me just say that there has been a lot of work, particularly in the theoretical computer science literature, in trying to find better and better algorithms to obtain to generate DPV samples. And there, in the last 3-4 years, there are new tree-based algorithms built on top of the classical spectral sampler, which gives a fast computational load of order m square log n or similar for each sample. So here m is the size of the sample you want to generate, and capital N is the size of the universal set you are dealing with. And I would like to say that the final word has not been said in this story, because every year there are improvements. There are these competing groups, some of them in Europe, some of them, I think Anari's group is based in Stanford, and they keep on improving. So for example, we do not know whether there is a lower bound to this, for instance. Okay. Yeah. So this is the situation in the sampling. The classical sampler and the new sampling techniques are actually built on top of the classical sampler. So they use the intuitions from the classical sampler, but geometric intuitions from the classical sampler, but in a much more clever and economical way, using tree structure. So this we will come to in more detail in the next lecture. And yeah, so there is less than 1 minute remaining, so I will not move to the next topic, and I will pause here. So we will continue from here on the next day, and the first thing we will take up is statistical learning theory with this kind of strongly dependent samples. Yes.
Yeah, so I guess this is a broader question. So what was the motivation of the TCS community in looking at this question?
Ask the TCS community. I think I think it's, I think it's, so these determinant models, for example, they have a very deep connections with combinatorics and metroid theory. So that's something which is very much in their ballpark. And besides this being a very clean mathematical model where many fundamental questions are basically unknown or known only at the very basic level, it has very deep connections to metroid theory. And these are all connected to all these strongly Rayleigh measures and so on.
So what kind of kernels do they consider? I mean, do they also look at your orthogonal polynomials, or?
No, orthogonal polynomials is more of a continuous space thing. In our experiments, we have found that actually discrete orthogonal polynomials work really well. They give you actually good, really good results in terms of approximation guarantees. But in this kind of business, what you can prove is strongly dependent on the setting and the toolbox you can bring to bear. If you are in continuous space, then orthogonal polynomials, if you, so for instance, it's like a beast. So for instance, Barry Simon has this entire thick book on orthogonal polynomials on the unit circle, just on the unit circle. So yeah, so you are basically standing on the shoulders of giants. Whereas in more unexplored settings, you are essentially out in the woods by yourself. So you have much less machinery. But I believe that slowly this will develop and grow, and more tools will be.
Other questions?
Yes. Yeah, so that's an excellent question. So that's those are the kind of the so if you tell a sampling theorist how to bake in repulsion into your model or system, then that's what we would naturally do, right? But usually these techniques are very ad hoc and not very tractable, in the sense that suppose I demand that, okay, you are locally inducing repulsion. Do you have a guarantee that it has a repulsion at the global scale? So here, for instance, this has repulsion at all orders. So any subset of any size with points, candidate points lying in any part of the space.
No, my point was, if you want to generate samples from this kind of kernel,
yes,
can you do it through some local movement? Start with a kind of randomly distributed sample.
I mean, I think I think the question is up in the air. So, for example, a very related and I would think a very related and relevant question is whether you can do a Markov chain Monte Carlo way, MCMC way, like a dynamic sampling algorithm here, right? I think I have seen only one paper on that, and that basically scratches the surface. So anyone who is interested in implementing this Markovian dynamics based
No, but Markovian dynamics will generate independent samples, right?
No. You have to tailor it so that it generates this kind of samples.
That's right.
So that's the problem. That's the thing to do.
Kind of in the spirit of what I'm saying. You kind of, but
yeah. Yes, but yes, it's a very relevant and important question, but one that hasn't really been looked into, to my knowledge. Yeah.
Thank you.